I'm going to continue working on the review questions from the quarter test review. I actually had a couple of integrals left, so I thought I'd go ahead and take care of those first. I think number 26 is the first one that I had not gotten a chance to look at, so why don't we take a look at that one. 26 is the integral of x times the quantity x squared minus 4 quantity cubed dx. And you can see for this integral, there's a product. I can't distribute it because of the third power function. I don't want to multiply out that using FOIL. But notice the derivative of the inside function here is 2x. So I need that x on the outside there, and I have it. But I don't just need an x, I need a 2x. So I usually will move the x over here. I need a 2x as the derivative of my inside function, so I'll multiply a 2 in there. I have to balance that by multiplying by 1/2 out in front, and now I should be able to reverse the chain rule, and I should be able to go through the antiderivative process. So inside function doesn't change, raise the power by 1, divide by the new power, and then we've got that 1/2 out in front. I would probably simplify a little bit. A half times a fourth is 1/8. You could write all of this over 8, or you could write it as 1/8 times the quantity x squared minus 4 to the 4th power plus c. Of course, if you have time, you might want to take the derivative and show that the derivative really does give you back the original function that I was given, if you have time to do that. But that's number 26. Question 27. Question 27 looks like it's going to be really challenging. It's actually not terrible. It's tangent cubed of x, secant squared of x, dx. And of course, tangent cubed, that's the quantity tangent of x, quantity cubed. So your inside function is the tangent function. Notice the derivative of the inside function, the derivative of tangent of x, is secant squared of x. I've got what I need to reverse the chain rule. I'm basically done. The derivative of the inside function is secant squared of x. That'll go away when I reverse the chain rule. And then I just have to reverse the power rule. So I'm going to raise the power by 1. I'll divide by the new power, and I'll add c, or you could write that as 1/4 quantity tangent of x to the 4th, or you could write that as 1/4 tangent to the 4th of x plus c. But anyway, pretty straightforward as far as integrals go. All right, I have two problems here, number 28 and number 29 from the quarter test review. The first one asks me to find the average value of this function. So the whole idea of average value is you've got a function, it's maybe some kind of parabola, it's changing, it's got infinitely many points over the course of the interval. So I can't add up infinitely many points and try to average those infinitely many points. But what I can do is I can use the average value of a function formula. I can take the integral of the function from some beginning point to some ending point, and I can divide by the length of that interval. And what that essentially does is I have some kind of a curved function. It finds the area under that curve, and it basically determines if I was going to change that to be a constant function, where would that function have to go to give me the same area under the curve? So we're breaking the curve up evenly over the interval. That's really what's happening. So anyway, to set this particular one up, I would take the integral from 2 to 5 of function x squared plus 4x plus 1, technically dx. And I divide by the length of the interval, which in this case is 3, 5 minus 2. And you should be able to do that relatively easily on a graph calculator. You can apply the fundamental theorem here. This one wouldn't be terrible with the fundamental theorem. But just to save a little bit of time here, I'm going to go to the calculator on this. And anyway, the integral from 2 to 5 of x squared plus 4x plus 1. The integral is going to be 84, and then I'm dividing by 5 minus 2, which is 3. So we get 84 thirds. If you want to divide that out, 84 is actually divisible by 3, and so the average value of that function is actually 28. Okay, so very straightforward formula to work with. Average value, pretty much a plug and chug kind of thing. Be careful though. Make sure that if they ask you for the average value, or for example, they could have asked for average velocity here, make sure it's the same information as what the function gives you. So if they ask for average velocity and they give you a velocity function, use the average value formula. If they ask you for average acceleration and they give you an acceleration function, use the average value formula. Watch out though, they could be asking you for an average rate of change. If they give you a position function and they ask for an average velocity, you're finding the average rate of change of the velocity, which is a different formula. That's basically a slope. So be careful. The function needs to be the same as whatever you're finding the average value of. Okay? Second scenario down here, number 29, we've got a velocity function here. I forget what the units are. You can look at the worksheet for that. But big thing is you've got this kind of progression. The rate of change of position over time is the velocity. The rate of change of velocity over time is the acceleration. So you're taking the derivative of position to get velocity, derivative of velocity to get acceleration, or you can go backwards. If they give you acceleration, you can take the antiderivative to get velocity, or you can take the antiderivative of velocity to get position. And you should expect to be able to start with any one of those equations and find the others if you're given the appropriate information. So first one here, we're finding the acceleration at 4. That's the same thing as the derivative of the velocity function at 4. The derivative of the velocity function, real simple. It's actually just 6. So I don't even have to substitute anything in there. That's very straightforward. The second part here, I'm asked to find a position function. A lot of times they use an S for that. Notice that they give me an initial value. That's because I'm going to have a constant when I take the antiderivative. Okay, so probably the simplest way to do this is a pretty easy function to integrate. So I'm going to go backwards here from velocity to position. So S of t is going to be the antiderivative. Raise the power by 1, divide by the new power. That's going to be 3t squared. Antiderivative of 5 is going to be 5t. Notice we're working with a t variable here. And you need a constant that's just a c value, okay? They tell me that S of 4 is equal to 10, so I can't just slap a 10 in there. I do need to actually substitute this in here. So in this particular case, I'm going to have 4 squared minus 5 times 4, and then add c, and I need to get a final position of 10. So 4 squared is 16 times 3 is 48, minus 20. 48 minus 20 is 28. And then I need to have this work out to be 10. So 28 minus 18 is going to give me my value of 10. And so C is going to be negative 18 in this particular case. So that's the particular solution for this position equation. And now I can find my position in any particular place. This question asks me to find the position after 8 seconds. So I can substitute 8 in here. I can substitute 8 in there. So that's going to be 3 times 64, which is 192, minus 5 times 8, which is 40, minus 18, and the correct answer there should be 134, whatever the units are for that particular question. Looks like the position is going to be in feet, okay? So it'll be at position 134 feet after going through that process, okay? Continuing with this problem, there's actually another part. Try to take a look at that as well. The last part asked me for the displacement between 1 and 5. Remember that displacement includes the fact that your function may be positive or negative. So I don't need to worry about making anything positive. Displacement, I can just take the integral from 1 to 5 of my velocity function, okay? We can think of this as an accumulating function. There's change taking place with that velocity. There's change in position. The integral allows us to add up, to accumulate that change that takes place over the interval from 1 to 5. So we'll take the integral of 6t minus 5 dt between 1 and 5. And again, if I kept my equation up there, I could have just used that, but we can also go to the graphing calculator for this. 1 to 5, 6t minus 5, and I end up getting a displacement of 52 feet, okay? Whether or not I have positive or negative values, I may get some things that cancel out. Distance, you're assuming that your velocity is always positive. Everything is considered to be counted, so you're not going to have offsetting positive and negative velocities. So you're not taking the absolute value of the final answer because you've already had those positives and negatives cancel each other. you want to take, for distance, you want to take the absolute value of the velocity function. You want all positive velocities from the start. Again, if you can, you want to do that in your graphing calculator. If you don't have a graphing calculator, you probably need to draw a picture of the graph, or you need to factor and find out where it crosses the x-axis, and you need to find the positive integral regions, and you need to find the negative integral regions, and basically you're going to have to make those negative regions positive and add everything up separately by hand. But anyway, I don't have any kind of restriction on this particular problem, so I can take the integral from 1 to 5. Absolute value should be under the math number button on your graphing calculator, and just type everything in here. And in this case, I'm going to get, well, that's kind of boring. Ends up being the exact same 52 feet that I had for the displacement. So a lot of times it's going to be different, but apparently, oh yeah, these values for the velocity are all going to be positive. So anyway, not anything real exciting in that result, but that takes care of problem number 28 and problem 29.